So now we know the Laplace transform of e to the at is equal to 1 over s minus a, and it converges for s greater than a. So if a is a complex number, then the condition for convergence is s greater than the real part of a. We need this because we want to talk about sine and cosine and recall the Euler's formula, which tells us that e to the I times k times t is equal to cosine kt plus I times sine of kt. And if we replace the exponent by its negative, then we have e to the negative ikt. Cosine is even, so we still have cosine kt. Sine is odd, so we have minus sine I times sine kt. If we add the two things together, then we get e to the ikt plus e to the negative ikt equals to 2 cosine kt. And divided by 2 on both sides, we get cosine kt equals to e to the ikt plus e to the negative ikt over 2. And similarly, we have sine kt equals to e to the ikt minus e to the negative ikt over 2. Now using this, we can calculate the Laplace transform of cosine kt. So the Laplace transform of cosine kt is the Laplace transform of e to the ikt plus e to the negative ikt over 2. Because Laplace transform is linear, so this splits into two Laplace transforms. And then using the result up here, so this is equal to 1/2 times 1/2 times 1 over s minus ik plus 1/2 times 1 over s plus ik. And because we use the condition s is greater than the real part, and the real part of ik is 0 because it's I times k, so it's pure imaginary. Same thing with the real part of negative ik, it's also 0. So the condition for these two is both s greater than 0 for both of them. So now we can combine the two fractions. So we get 1/2 times the common denominator is s minus ik times s plus ik, and s plus ik plus s minus ik. So this is equal to 1/2 times 2s, and the denominator is s squared plus k squared. So this is equal to s over s squared plus k squared, and for s greater than 0. So that's the Laplace transform for a cosine function. And if we follow the same procedure, so similarly, the Laplace transform of sine kx kt is equal to k over s squared plus k squared, and this also converges for s greater than 0. So now we have all the important functions Laplace transforms. So if you go to your book, you will find a table. Let me just write down here. So here's the table here for Laplace transform. Okay, so now if I give you the random function to ask you to find the Laplace transform, let's say Laplace transform of e to the 2t plus 1 plus 2 sine squared t plus t times t plus 1. Then we first use the linearity to split it up. So this is the Laplace transform of e to the 2t plus 1 plus the Laplace transform of 2 sine squared t plus the Laplace transform of t times t plus 1. And we need to turn these functions into the things in the chart. So first, we use the fact that e to the 2t plus 1 is e times e to the 2t. And we also use the fact that 2 sine squared t is equal to 1 minus cosine 2t. And for the third one, we distribute the two terms. So we get t squared plus t here. Now, take the constant out, and then use the linearity again. So this is equal to e times the Laplace transform of e to the 2t plus Laplace transform of 1. 1 is t to the 0 minus L of cosine 2t plus the Laplace transform of t squared plus the Laplace transform of t. So now, every single term inside now can be found in the table. So we can do this directly. So what we get is this equal to e times e to the 2t is here. So it's 1 over s minus 2. This converges for s greater than 2. And the second term is t to the 0, which gives you gamma of 1 over s to the first power minus Laplace transform of cosine 2t, which is given here. So it's s over s squared plus 2 squared. This converges for s greater than 0, so it's the previous term. And the Laplace transform for t squared is gamma of 3 over s cubed. And the Laplace transform for t is gamma of 2 over s squared. All these converges for s greater than 0. And we know gamma of n is n minus 1 factorial, so we can rewrite everything. So this is 1 over s minus s over s squared plus 4 plus 2 over s cubed plus 1 over s squared. And the conditions combined together, we pick the more strict one, so it's s greater than 2. So this is the Laplace transform of this complicated expression.